So let's say we have these two coil loops next to each other, and they both have some constant current going through them. So in each coil, the current is going to make a magnetic field that goes around, and this magnetic field is also going to cause some magnetic flux in the other loop. So like the current in coil 1 is going to create a magnetic field, and then that magnetic field from coil 1 is going to cause some flux through coil 2. And right now, if the current is constant, then the magnetic flux in the other coil is also constant, so it's not changing. But if we make the coil through coil 1, the current through coil 1, say it's changing over time, then that means the magnetic flux that it causes through the other coil is also changing over time. And we know if the magnetic flux is changing over time, then there is an induced EMF. So the induced EMF in this case through coil 2 is just going to be given by Faraday's law. And the negative n, the number of coils, times the time rate of change of the magnetic flux. And so we can say that the total magnetic flux through coil 2, which is n times the flux, is directly proportional to the current in coil 1. Now this makes sense. If there's more current in coil 1, then the magnetic field is going to be stronger, and so the magnetic flux through coil 2 will be stronger as well. And we can call this proportionality constant the mutual inductance M. And so taking the derivative of both sides of this equation with respect to time, we can see that the induced EMF in coil 2 is equal to negative m times the rate of change of the current in coil 1. So of course we can also have the opposite thing happen, where the current in coil 2 is changing, which makes a changing magnetic flux through coil 1, and therefore induces an EMF in coil 1. And so if we were to do the same equation, you would find that the mutual inductance is the same in both cases. So for any pair of conductors, there is only one value of the mutual inductance. And from this equation, you can see that the definition of the mutual inductance is between these two conductors is the coils times the flux over the current in the other conductor. So N2 flux 2 over I1. And the unit of this mutual inductance is the Henry, which is H, and it's equivalent to Webers divided by amperes. So we can also have just one element with a changing current induce an EMF in itself, because if the current through a single circuit element, that's going to create a magnetic field and therefore a magnetic flux through itself. And so if the current is changing, then the magnetic flux that it's causing through itself is changing as well, which, as we know, induces an EMF. And this is called a self-induced EMF. So the equations are similar for the case of the mutual inductance, but instead of the M mutual inductance, we use the self-inductance, which is L. So L is a constant specific to whatever conductor is inducing an EMF in itself. So the definition of L, the self-inductance, is N, the coils, times the flux, divided by the current. And rearranging this equation and taking the derivative, we find that the self-induced EMF is negative L di dt. So again, there's only a self-induced EMF when the current is changing. So when it's constant, di dt is 0 and the self-induced EMF is 0. And again, that's because only when the current is changing is the magnetic flux changing through itself. And so when we just say inductance, we usually mean the self-inductance, not this mutual inductance. So now let's see how this concept of inductance applies to a circuit. So we're going to introduce a new type of circuit element called the inductor, which is symbolized by this little coil over here. And it's a coil because, as you can see, the self-inductance depends on the number of coils. So if we have a lot of coils, then this effect is going to be a lot more noticeable than if it was just a straight piece of wire. So the whole point of an inductor in a circuit is it can resist changes in current. Remember Lenz's law, it says that the self-induced EMF is going to be so that the magnetic field is going to oppose whatever caused the original induced EMF. So in this case, the cause of the induced EMF is a changing current through the circuit. So let's say the current is increasing through this inductor. So the induced EMF in the inductor, by Lenz's law, it's going to oppose that increasing current. So it's going to slow down the rate at which the current is increasing. And so when we have an inductor, the current will not be instantaneous. You know how usually if you just have a regular circuit, you can assume that as soon as you close the switch, then there's immediately a full current throughout the whole circuit. Well, if we have an inductor there, then it's going to make sure that the current increases gradually. So as we close the switch, the current will still be 0, but it will keep increasing until eventually it reaches its maximum value. And so when there is a changing current through an inductor, then there's a potential difference across it. And this potential difference is equal to the self-inductance L times the rate of change of the current. And so the reason that this potential difference is created is because the inductor is storing energy inside it. So let's say we have a circuit, the current starts at 0, and it increases to its maximum value, capital I. And so we want to find out how much energy is going to be stored in this inductor as the current increases from 0 to maximum. So remember, by Joule's law, the power that a circuit element uses is the potential difference across it times the current through it, or in other words, I times delta V. And in plugging in this expression, the potential difference across an inductor is L times di dt. We get this expression, and then since power is the time derivative of the potential energy, du dt, you can multiply both sides by dt to get du is equal to Li times di. So now to find out how much energy is stored as the current increases from 0 to its maximum, we just integrate both sides of this equation. So if we integrate du, then we'll just get the total energy, and then we integrate Li di from 0 to the maximum current. And so we get that the total energy stored in the inductor is equal to 1/2 L times I squared, where I, remember, is the maximum value of the current in the circuit. And we can find this maximum value of the current by using Ohm's law. It's just going to be the EMF divided by the resistance. And that's because when the current reaches its maximum, that means it stopped increasing. In other words, di dt is 0. And so when the current is constant, there is no potential difference across the inductor, and therefore it doesn't have any resistance. It just behaves like a wire. And so we saw how the inductor can slow down the increase of current in the circuit when it just starts, and it can also slow down if the current is decreasing. So say the current starts out at its maximum value and it's decreasing to 0. So the inductor is going to slow down this process by releasing the energy that it stored in itself while the current was increasing. So when the current decreases, the inductor is releasing energy, which contributes to the current a little to stop it slowing down. And so it turns out this energy that's being stored in the inductor is basically being stored inside its magnetic field. Remember, when the current goes through the inductor loop, it creates a magnetic field. And so this is similar to how a capacitor stores its energy inside the electric field between its plates. So we can find an expression for the magnetic energy density of this magnetic field, which is the energy inside the field divided by the field's volume. So it's the energy per unit volume stored inside this magnetic field within the inductor. And so it's equal to B squared, which is the magnetic field, over 2 times mu naught, which is the permeability of free space, that constant.